Good morning, everybody. Last week we were discussing the virtualization topic, and we said that at the center of these virtualization concepts, we have the hypervisors. Remember the name hypervisor? It comes from the supervisor. Supervisor in an operating system schedules between the processes. Hypervisor in a computer system schedules and manages the operating system on a single computer. Okay, we said that there are two types of hypervisors: type 1 hypervisor and type 2 hypervisor. Type 1 hypervisor works on the bare hardware, and it just shows itself. It just appears as the hardware to the guest operating systems. Okay, these are the guest operating systems, and this is a guest operating system. So the operating system Windows thinks that it is running on standard hardware, but in fact it is not. Type 1 hypervisor makes this illusion that Windows works on the hardware. So this kind of technique has several advantages. We call this virtualization, and we talked about the advantages. You might say there might be some disadvantages. Yeah, what is the disadvantage? The disadvantage is obviously like the operating systems. Okay, this is a piece of software. So if it's a piece of software, it has to run on the hardware. So on top of the useful stuff, on top of the useful stuff, I have to run this operating system and this hypervisor. Okay, so I will be less efficient. But if you think about the alternative is to have a separate machine for each operating system. Well, using a single computer is more efficient than using two computers, right? You don't need separate hardware, and we talked about also. That's why people like virtualization technique a lot, and we use it in our classes. We use it in our software development efforts, because I mean, if I am developing software for Linux, I don't have to have a Linux box. I can do this virtualization, and I can develop my software on a Windows box for the Unix, and I can test it. I can do all that kind of stuff, like we're doing for our homework. Okay. So these were the things that we talked about yesterday, last week, sorry. And we talked about the advantages and the requirements. And so let's look at this virtualization techniques again. So actually the virtualization, last time we talked this, we did not talk about this much. Virtualization has several components. The most important one is the virtualization of the CPU, right? I mean, this one here, this Excel document should think that it has its own CPU. Whatever it executes, it will be executed. As long as it is not executing any privileged instructions, it should be fine. And Windows makes sure that, the operating system Windows makes sure that this Excel stays within the bounds of its capabilities. It should not execute any specialized instructions and etc. On top of it, this hypervisor should make sure that this Windows doesn't do anything harmful to the other operating system or other virtual boxes. Okay, other virtual operating systems. So these all have to be done by Windows and the hypervisor, but the Windows doesn't know, the operating system doesn't know that there is a hypervisor. Okay, so this should be done independent of Windows or Linux. I mean, as a hypervisor, you cannot get help from Windows or Linux. Okay, That's what I am saying. So I have to virtualize the CPU. So how should I do that? Okay, that's the first thing. Virtualizing the CPU. That's what we did at the beginning of the semester, right? With the idea of the processes and the threads, we virtualized the CPU, and then we said that maybe we should do the similar stuff for the memory. Okay, so we came up with the idea of address spaces for the memory, and hypervisor should do the same thing too, because if you don't virtualize the memory, then I will be in trouble between these two operating systems. And similarly, I should be doing something about the virtualization of the I/O devices. So three things has to be done by these hypervisors: virtualization of the CPU, virtualization of the memory, and virtualization of the input-output devices. Okay, that's what the hypervisors do. While I am saying that, doing these three kind of virtualizations, of course, it is not easy, but it is not as difficult as detailed virtualizations or detailed abstraction of operating system virtualization of the CPU and the memory and the I/O devices, because these type of hypervisors, they don't have to know many things about the I/O drivers. They don't have to know many things about the scheduling and other related stuff. Definitely, they don't have to know anything about the user interfaces. Okay, uh, 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 all they have to interact with operating systems. Okay, not user processes, not the user itself, etc. So these hypervisors are much simpler than the operating systems themselves. That's why we say that if on this box, if on this picture, if any software crashes, if any piece of software crashes, it is most likely these operating systems or one of these applications. The least likely faulty software will be this hypervisor here, because it's a simple software. I mean, compared to other ones, they are simpler, and you don't expect. Of course, bugs happen, but the likelihood that you have a bug in the hypervisor is much smaller than you have a bug in Windows or Linux. Okay, so virtualization technique. So let's start from the CPU. Okay, so what we do, consider each instruction in an interpreter. So we are doing something, an interpretive technique. Okay, and the interpreter, let's say, are type 1 hypervisor. Let's talk about the type 1 hypervisor. This is hardware. This is type 1 hypervisor, and this is Windows, and this is Linux. And these are my applications. Application, 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 and application. Okay. If Windows operating system is executing an instruction, this type 1 hypervisor, as an interpreter, if you like to think it as an interpreter like the Java virtual machine, it takes that instruction, okay? It takes that instruction and it interprets it. What do you mean by interpret? Okay, it is executing, it is doing whatever that instruction wants, okay? Some of these instructions can be executed directly on the hardware, okay, because you don't have to do anything about this increment instruction. That application tries to increment a register, that's fine. Okay, so for those kind of instructions, this type 1 hypervisor don't do anything at all. Okay, but if the instruction is a privileged instruction, Windows tries to execute a privileged instruction. What does the first of all, I mean, if the application is executing such an instruction, then that's a bad thing. That application has to be stopped. But if Windows is executing a privileged instruction, like modifying the page table or disabling the interrupts and etc. Okay, this type 1 hypervisor cannot let it run on the bare hardware, because that will be problem. If this Windows disables all the instruction for the whole machine, then Linux will be in trouble then, right? So I cannot do that. So it has to be interpreted. This type 1 hypervisor has to find a way to disable the instructions for this part of the system only, for the Windows part, without actually disabling it for the whole computer. Okay, so this is basically what the CPU virtualization is all about. Okay, this is very I mean, the concept wise it is simple. Of course, when it comes to implementing these, it is not that simple. And last time we talked about it, and the virtualization method. Okay, and types of available virtualization packages. Okay, type 1 hypervisors and type 2 hypervisors. We are going to talk about them a little bit later, and we talked about this last time actually, and I'm not going to talk much about. Let's talk about this para-virtualization. Okay, this para-virtualization says that, remember what we said before. We said that okay, we said that Windows or Linux here, or the guest operating system here, don't know about what kind of environment they are running on. They think that they are running on the bare hardware. But in fact, by looking at this picture, this Windows and this Linux is running on this type 1 hypervisor. Okay, the para-virtualization says that, okay, what if we change this way of designing operating systems? Okay, let's say we don't want to write the operating systems that way, and we are not going to let operating systems to access the I/O devices directly. We are not going to let the operating systems change page tables directly, but instead we will ask the operating system to make hypervisor calls. Okay, like a regular application making a system call. Okay, we will ask the operating system to make a hypervisor call. Okay, this is called para-virtualization. That means what? Okay, in this case, on the left side of this picture, this Windows don't know that it is running on a hypervisor. Okay, so the task of this hypervisor is difficult because it has to emulate the whole hardware. But here, this sometimes this can be called a microkernel. This microkernel and the modified Linux know that they are doing this. Okay, this one says that, okay, I am going to emulate this hardware for the upper layer software, which is the operating system, and this modified Linux knows that it is not running on the bare hardware. Okay, it is not running on the bare hardware. So this Linux has to be modified. This has to be a modified Linux, and this modified Linux, whenever it needs to do the privileged stuff, it doesn't do it itself. It does that. By asking the hypervisor, the specialized hypervisor, or the para-virtualization layer, software layer. Okay, and para-virtualization makes these kind of virtualization a lot more efficient. Why? Because these two can communicate, and this one doesn't try to. I mean, the things that the modified Linux asks from the microkernel doesn't have to be interpreted. They can communicate much efficiently. So what was the problem with the virtualization? The problem with the virtualization was it was inefficient. Why? Many things has to be interpreted. Many things has to be emulated through software. Now I don't have that problem. Plus, I have all the advantages of virtualization. I have all the advantages of virtualization. So that means that I have the best of both worlds, and that's a very good idea. What is the downside? Downside is you will need this modified Linux. Okay, you will need modified Windows. You will need modified operating systems. And no problem with Linux because I have the source code for the Linux. Okay, but for Windows, for the Mac OS 10, I need help from the Apple or Microsoft. Otherwise, I cannot go on. Okay. By the way, such modified Linux is available. It's an extension, and you can have those kind of Linux configurations to run on these kind of microkernels. Okay. So that's what we do with the para virtualization. And whatever I do with the modified operating system, it is not called system call anymore. It is called hypercalls. Okay, it is called hypercalls. Okay, so that's what we said. Okay, so since we are talking about the virtualization, and virtualization has to be efficient. Let's talk about it a little bit more about the efficiency. Last time we talked about this a little bit actually. Virtualization support by the hardware is important, especially for the CPU virtualization. Without the virtualization support, the hypervisor has to do a lot of things. One of them is, of course, is emulation of the privileged instructions. But how do you know that? Okay, how do you know that the guest operating system or the application is running a privileged instruction? Okay, privileged instruction. With the hardware support, the CPU will trap to the kernel, saying that somebody tried to execute a privileged instruction. Okay, that's what the virtualization support is mainly. So whenever this application 1 or this Windows operating system executes a privileged instruction, then the CPU traps to the kernel. Okay, so this is the kernel. Okay, CPU traps to the kernel and lets the hypervisor know that somebody is trying to execute the privileged instruction. If A1 is trying to execute the privileged instruction, all hypervisor do is let Windows know about this. Okay, so it is going to run the regular application doing bad stuff. But if the Windows is running this specialized or privileged instruction, then hypervisor has to emulate this. Okay, hypervisor has to emulate this. So I get help from the hardware, and I would know that whenever I need to do this emulation. Okay, if I don't have to do the emulation, I will let the normal application and the Windows run. Okay, this is what we say virtualization support. And currently, for the last 10-15 years, our main CPUs, Intel CPUs, AMD CPUs, they support this virtualization technique, VS. Okay, and that makes our virtualization jobs a lot easier. Okay, a lot easier. So this guest operating system, of course, tries to run privileged instruction, but it cannot, and it has to trap into this hypervisor. That's we do this with the help of the hypervisor. Okay, the thing here is that this, okay, maybe, I mean, from the beginning of the semester, we wanted to draw this stack of hardware operating system. This is hardware, okay. This is my operating system, and these are my applications. Application 1, application 2, and application 3. I don't know what this upper part is. Okay, okay, so this is the picture. That's what we did from the beginning of the semester. But I mean, when it comes to virtualization, maybe it is better to think about this picture as like this. As like this. The real picture maybe is just this hardware, and there is this operating system, and again I did it wrong. Okay, there is this operating system, there is this application 1 and application 2 and dot dot dot, and the communication between the hardware and of course the operating system is direct. And actually I am doing kind of the same thing with the application 1 and application 2 whenever it comes to the execution of the instruction. So application 1, application 2, okay, most of the time don't need any operating system intervention. Okay, they directly run on the hardware, they increment the registers, they copy the registers, they do the multiplication and etc. Right? So they don't need much operating system help. But whenever they need the operating system help, okay, so they communicate with the operating system by doing this system call. And actually the system call goes this way. Let me not draw that way, but I should do it this way. So it goes that way, and it goes that way. Why? Because A1 says that I'm going to make a system call. System call is handled by the hardware actually. Okay, you make a system call. Hardware says that okay, it's a trap to the kernel, and I know what part of the operating system I'm going to run. So it jumps that part of the operating system. So this is the real picture actually. So when we say application 1 is running on top of operating system, this is not exactly true, because this looks like, I mean, this looks like a remember our this is we used to draw this picture before. Okay, this is hardware, this is operating system, this is Java virtual machine, and these are our Java applications: Java application 1, Java application 2, Java application 3, etc. Okay, so each of these Java applications needs the Java virtual machine for every instruction. I mean, this upper part of the picture is correct. Okay, so they run on top of Java virtual machine. This is perfectly correct. But this is not perfectly correct, because application 1 does not need the operating system's help for many executions of the instructions. When do I need the operating system help? I need operating system help when I need to do some input-output stuff. So I ask the hardware to get some help from the operating system. This is the real picture actually. This is the real picture. So if you think about it this way, virtualization techniques kind of makes more sense, because most of the time I am executing my instructions on the bare hardware, but when it comes to doing some specialized instruction executions, I need the operating system help. Okay, and the virtualization kind of extends this idea. Virtualization says that, okay, I will extend this box a little bit, especially type 1 hypervisor, type 1 hypervisor, and it is running again on this hardware, the same hardware, and most of the time this application 1, application 2, or this operating system is running on the hardware, but whenever they need to run specialized instruction, including the operating system, they need to make a call to the type 1 hypervisor. Okay, and of course A1 doesn't know about the hypervisor operating system. Operating system doesn't know about it, but it communicates with the type 1 hypervisor with the help of the hardware. This is what is happening actually. So the virtualization uh, is not like the Java virtual machine virtualization, but most of the time our user processes are using the CPU directly. Otherwise, if I interpret each instruction one by one like the Java virtual machine, that would have been very slow, very slow. We wouldn't do that, okay? And this virtualization supports make this picture a lot easier, okay? But the thing is that before the virtualization support, before the virtualization support, we did not have any easy way of achieving this. So what did they do? Okay, what did they do? Of course, before the virtualization support, we had the virtualization software like those hypervisors. Okay, so they came up with some clever solutions. The basic solution was this. They said that before the application runs, I will rewrite this application. Okay, so rewriting of the code. Okay, rewriting of the code. Rewriting of the code is like this. Okay, let's say my application is. This is my application, and these are my. Why don't I use the blue color? Okay, my application, and these are my instructions one by one. Most of the time these are very simple instructions such as incrementing the registers, adding two registers together, multiplication, exclusive ORing stuff. Okay, so I get the original application, and inside my original application I have these kind of loops maybe. Okay, here I have branching another branching. So I take this kind of application, I rewrite the executable code. I am not talking about the source code, but the executable code, in a way that I make them into execution blocks. Okay, I say that. Okay, I say that this is a basic block. This is a basic block. This is another basic block, and etc. Okay, so I separate them into basic blocks, and I know that this part of the application can run on the CPU without any problems. So I am not going to interpret any of these instructions. I will let them run on the CPU itself. Okay, so this part of the code doesn't need any virtualization. Okay, so this technique is called rewriting the code. So converting your code into basic blocks, and that's the definition of the basic block. It's a short straight line sequence of instructions that ends with a branch. Okay, so this is called dynamic translation and emulation. It sounds expensive, but most of the time it is not, because once I translated those blocks, they are cached, I don't have to do the retranslation all the time. Okay, so whenever I need to run that block again, I have I have that in my cache. Okay, and I am using those blocks from the cache from the cache. And they took advantage of the Intel CPUs. Intel CPUs for a long time they supported this idea of ring 0, ring 1, ring 2 and ring 3 levels of protection. But Windows operating system or Linux operating system did not use this ring structure. They only use this ring 0 and ring 3. Okay, ring 0 is the kernel mode and ring 3 is the user mode. Okay, they did not support it. Do you remember where these ring names come from? Do you guys remember the ring names, where the ring names come from? Ring 0, ring 1, ring 2, ring 3. I think we talked about this at the beginning of the semester. There was a place where the names of the rings came. This idea was introduced by one operating system. Do you remember the name of the operating system? What is the most influential operating system out of all the operating systems that we have studied historically? What operating system made the most contribution to the ideas of the operating system concepts?
Is it Multics?
Yes, Multics. Yeah. Okay. Good answer, Emek. Well, I mean, that's not a very difficult question, and we didn't talk any other historical operating systems other than the Multics. Yeah, it was the idea of Multics. Okay. Remember, Multics developed with along with his hardware, and this ring structure were available in Multics, and Intel made these ring structures available, but nobody had used it. So without the virtualization support, they had these stuff. Since the Windows or Linux did not use any of them, the hypervisors were free to use this kind of structure, and they took advantage of it. So this hypervisors, type 1 hypervisor, put the guest operating system in ring number 1. So there is a privilege classification difference between the regular applications and the guest operating system. So that made it kind of more manageable for the hypervisor software developers. Okay, so even if you don't have the direct virtualization support from your hardware, these ring structures were available for you, so you can take advantage of it. Okay. So the virtualizing the unvirtualizable by unvirtualizable, we mean that it is not unvirtualizable, of course. I mean, the worst that you can do is this. Okay, the worst that you can do is use exactly the same idea. Interpret each instruction one by one. Okay, interpret each instruction one by one as a hypervisor. That would be a solution, but that would be too inefficient. But it would be an acceptable solution. I mean, if why? I mean, I can accept how Java is doing it, right? I say that okay, Java is doing it. Why can't I do this for the operating systems? That would be a little bit slower, 2 times, 3 times slower than the usual. But we don't have to do that. Okay, we have help from the hardware, either in the form of virtualization support or other types of support. And even if we don't have any support, we can do this. We can do this basic block, okay, basic block analysis of the code. and we can do the virtualization that way. Okay, good. So we kept talking about type 1 hypervisors because it is easy to talk about them. Okay. Type 2 hypervisors are actually maybe more common, or at least they are easier to use. All you need to do is to install your type 2 hypervisor on top of your operating system on top of your operating system, and it will show itself as the bare hardware to the guest operating system, and you install it. Okay, so to run your guest code natively and use exactly the same techniques requires a type 2 hypervisor to manipulate the hardware at the lowest level. Let's remember type 2 hypervisors again. So this is my hardware. This is hardware. This is my operating system. And this is type 2 hypervisor. And this is the application on top of the original operating system. And these are my other applications. Okay. So this application here doesn't know that it is running on a, I'm sorry, I made a mistake here. Let me put a guest operating system here, and this is an application 1 and application 2 and application 3. Okay. Application 1 doesn't know that it is running on a guest operating system. It just executes normally. And this is called type 2 hypervisor. The thing is this, okay? To make the things more efficient for type 2 hypervisor, when you install this type 2 hypervisor, you let the operating system know that you are going to do this. Actually, operating system is going to be like this, and type 2 hypervisor is going to have some direct access to the hardware. Okay, so type 2 hypervisor is running in the kernel mode, is running in the user mode like A3 or A4, but from time to time, okay, it has some direct access to the hardware, such as modifying the page tables, setting up interrupts, handling the interrupts, and etc. That's the type 2 hardware. Okay. Of course, operating system will not let any regular applications to do that. But when you install your type 2 hypervisor, this operating system will ask you many times, are you sure you want to do that? This type 2 hypervisor is going to this application. I mean, for the operating system, this is just an application. This application tries to modify some privileged stuff. So operating system makes sure that you know what you are doing. And this is the structure of the type 2 hypervisors. And when you do that, type 2 hypervisors become much more efficient. Of course, they are more complicated that way, but they will be much more efficient because most of the time, whenever they need to, they have the privilege of accessing the hardware directly. Okay, so that's called um, a hypervisor having a kernel module. You install it. It's like the driver. Remember the I/O device drivers? When you install an I/O device to your operating system, you have to provide the driver, which is a piece of code, right? So that piece of code becomes the part of the kernel part of the operating system. And this type 2 hypervisors are doing a similar thing. They say that, okay, I'm going to provide you some code, okay? This code will be part of the operating system, and I will use this code exclusively to access the hardware directly. That's what type 2 hypervisors do most of the time. They directly They directly run on the hardware. So they, in a way, they behave like the type 1 hypervisors, to make the things more efficient and effective. Okay, any questions so far? Any questions about type 1 and type 2 hypervisors and how we are dealing with them? Again, we did not talk about anything other than the CPU virtualization. Okay, all we talk about the CPU, all we talk about the executions of the instructions. And in a few minutes we will start talking about virtualization of the memory and I/O devices. Okay. So cost of virtualization efficiency is, remember at the beginning, this is 17, we said that there are things that we need to be careful about. Okay. Safety, fidelity, and efficiency in terms of virtualization. Okay. Fidelity, we cannot make any compromises on fidelity. I mean, whatever we are virtually providing, it should be exactly the same as the original. Okay. Safety, I should not introduce any safety problems by doing this virtualization. And efficiency. Okay. With the efficiency, my virtualized hardware should not be too slow. My applications that I am running on the virtualized hardware and the virtualized operating system should not be too slow. So I should be concerned about the efficiency. Let's talk about the efficiency, cost of virtualization. Okay, so the virtualization support lets me use this idea of trap and emulate. Okay, so what is the trap and emulate? Trap and emulate is this. Can anybody tell me what trap and emulate is? Trap and emulate. We talked about it a few minutes ago. Trap and emulate. It is simple again. It is just, the name says it.
Some of the actions may conflict with each other, sir, and host operating system will not be affected by the guest's stuff, and this is called trap and emulation.
So where does the trap come from?
Hypervisor.
Say it again. Where does the trap come from?
Hypervisor.
No. Who causes the trap?
Oh, I think guest operating system.
Yeah. So the guest operating system causes the trap. This is type 1 hypervisor, and this is guest operating system 1, and this is guest operating system 2. Okay. Normally these operating systems, they execute the instructions directly on the hardware, but if they try to, okay, this is the kernel part and this is the user part. If I execute an instruction that is a privileged instruction, it will cause a trap. Okay, it will cause a trap to the hypervisor, and this trap is, of course, it is supported by the hardware. When I get the trap to the hypervisor can emulate that specialized or the privileged instruction. And so that's the trap and emulation. Okay, privileged instruction causes a trap to the hypervisor and I emulate them. This is called trap and emulate, and it is possible because I have the virtualization support. But it turns out that, okay, this generates lots of traps, and traps are expensive. Why? Because when there's a trap, you need to save lots of stuff. When there's a trap, there is a cost of context switch. updating of the page table, translation look ahead buffers, and etc. Right? So that's costly. I mean, I get the hardware help, but it's still becoming costly. So some hypervisors say that, okay, I am not going to get that trap. Okay, I will do this binary translation, dynamic binary translation of the applications, and I know which instructions are going to cause a trap. I will not let them cause a trap. I will run that application up to that point, and I will do the emulation at that point. Okay. So some hypervisors, even though they can have the trap, without the trap, they prefer doing the binary translation, online binary translation. So with this approach, it turns out that things are more faster. Things are faster. Okay. Of course, it depends. I mean, depends on the emulation stuff and etc. So with the binary translation, sometimes things are faster, sometimes not. So even with the virtualization support, the hypervisors may prefer sometimes binary translation over the hardware help of trapping to the kernel. Okay, good. Okay, so if we return back to if we return back to this idea of using modified Linux, okay, and on top of a microkernel or the para-virtualization layer of software, that's the idea, para-virtualization layer of software, okay. What would be the disadvantages? The disadvantages, okay, of course, okay, you need to modify your operating system. All the sensitive instructions are replaced with calls to the hypervisor, okay. And if you do that, if you modify all of your operating system that way, then there is no way that these kind of operating systems will run on the bare hardware, right? I mean, this modified Linux needs definitely this kind of a layer of software, okay? So that would be one of the problems. The other problem is, okay, I mean, depending on your hypervisor here, okay, uh, if you have different type of hypervisors, I have to modify my Linux or my Windows or my other operating systems differently for VMware or Xen or Microsoft Hyper-V and etc. So each one would have a different API, and that would be a problematic thing. Okay, so they end up doing this. Okay, virtual machine interface. Okay, so there is a virtual machine interface library. You put this library between your modified Linux and your hardware, or modified Linux between the VMware, or the modified Linux between the Xen hypervisor. Okay, so you are making this translation because the API for this one is different and this one is different, and there is no API for this one actually because it is running on the bare hardware. So that's called the virtual machine interface. They say that, okay, let's do it this way. Okay, modify the Linux in a standard way. The modified Linux thinks that it is running on this virtual machine interface, and then somebody has to convert all these API calls to the other types of hypervisors. So I mean, you might think that this is getting out of hand. Okay, I have I have hardware, I have a hypervisor. On top of the hypervisor, I have the interface to the hypervisor, then the modified operating system. Yeah, but usually that's what happens with the virtualization. Okay, once you start doing the virtualization, okay, you will never stop. You will put one more layer of virtualization on top of each other. Okay, things may become more inefficient, but if there are advantages of doing it, then nobody is going to stop from doing so at the cost of a little bit efficiency maybe. Okay, so this was some of the disadvantages of the microkernel as the hypervisors and some solutions for them. Okay, so up to now, as I said before, we talked about the virtualization of the CPU. By the way, I will not give any breaks today because I don't have much to say about the rest of the chapter. We will talk about the virtualization of the CPU and virtualization of the I/O stuff. Okay, and after that we will stop. So I will stop early and I won't give any breaks. So up to now we talked about the virtualization of the CPU. How about the memory and the I/O devices? Memory and the I/O devices. You might say that, okay, memory is already virtualized. Why? Because we have our page tables and we get our help from the hardware to handle the page tables, but our memory management unit doesn't know about our virtualization of the whole operating system. Okay, and if we have more than one operating system running on top of our hardware, each one will want to modify the page table for their own purpose. So they are kind of will interfere with each other, and we don't like that. That's why for each virtual machine, hypervisors need to create a shadow page table. Okay, what do we mean by page table? So kind of they are taking the backup of the whole page table, or maybe they are doing this. Okay, maybe they are doing this. Previously we had the physical addresses and the logical addresses, right? Now we have, okay, guest virtual addresses, and for the guest virtual addresses there are guest physical addresses, but these guest physical addresses are not real physical addresses actually. These are the virtual addresses of the real hardware. Okay, so 3 levels of address space: guest virtual addresses, guest physical addresses, and machine physical addresses. Kind of confusing, but if you don't do this, then memory virtualization will not be done. Okay, so there is this idea of guest virtual addresses. These are the addresses used by the applications, and then I have the guest physical addresses. These guest physical addresses are used by the host operating systems, and then I have the host physical addresses, or the machine physical addresses. These machine physical addresses are used by the hypervisors. And without getting hardware help, to switch between these address spaces, my job would be difficult, and that's why I get this hardware support. And this is the picture actually. Do you guys remember this picture? I mean the upper part of it. Where did I get this picture? Remember? What structure was this? From 0 to 11 page offset, and the level 4 offset, level 3 48 bits. This is the Intel virtual address, Intel processor virtual address structure. 4 levels of page tables, remember? 4 levels of page tables, and each one has 9 bits, if you remember that. Okay, so this is the picture. When you get the offset from the level 1, okay, you get that offset, guest pointer to the level and page table, and then you make a lookup from the guest operating system's nested page tables, and you get your result, and then you make another level of lookup. Previously we didn't have this part. Whatever we had from this point, it was used for a lookup like that. Now I have to make another lookup in a guest, okay, in another page table. So this kind of memory virtualization is possible now. Okay, so this is hardware support for nested page tables, and hardware knows that I am running this virtualized environment, and it makes necessary adjustments in the of course hardware, the page tables, and all of my page tables, all of my loaded pages, physical memory and logical memory, they all are managed with the help of the hardware. Okay, so this is going to make my life a lot easier in terms of virtualizing the memory for the guest operating systems. Okay, you might think that handling this was very expensive in terms of hardware. Now I am adding this, but I mean that's the cost of making a progress nowadays. I mean, our chips are not getting any faster. We keep using the same speed chips for the last 10 years, 15 years. So where does the progress come from? Progress progress comes from this kind of support. Okay, you add more capability to your page tables. Okay, now I can do uh, uh, hypervisor support for the CPU and for the memory directly on my hardware. Okay, my hardware doesn't become faster, but it is more capable. Okay, and now it is possible to use reliably and efficiently a very useful technique called virtualization. Okay, without much problems because of these kind of additions. Okay, so hardware makes this addition for you. Another okay. Uh, of course, there are issues with the virtualization support for the memory, like the how much memory should I allocate to each of the host operating systems, and how many pages should I keep for each of them, because the host operating system doesn't know that it is running on a virtual system. uh, uh, that's going to be a problem because the communication is only one way. uh, Communication is only one way. Those kind of problems has to be solved. I mean, I cannot, as a hypervisor, I cannot tell the operating system to use more memory or to use less memory. Okay, because the guest operating system doesn't know that it is running on top of an hypervisor. So what do? They use a technique called ballooning. Okay, there is a ballooning. Okay, ballooning is a technique where, okay, this is what it does. Okay, this is my hardware again. I am drawing this picture for the 40 times. Okay, maybe this is type 1 hypervisor. This is the guest operating system 1 and guest operating system 2, application and application. So there is a ballooning application and there is another ballooning application running on these guest operating systems. This type 1 hypervisor directly communicates with these special applications running on top of guest operating systems, and their task is to allocate memory for nothing. They don't use the memory. Okay, they balloon, they make them larger, then they make them smaller. So in order to manage the memory between these two guest operating systems, okay, the type 1 hypervisor says that, okay, although you don't need that kind of memory, I am going to inflate this balloon so it shows it larger than it needs to be. And sometimes okay, they say that, okay, you are too big, I am going to deflate this balloon. And so they have to find these kind of tricks. The guest operating system, neither of them, okay, they don't know anything about these balloons being special. They think that these are some application that needs more space or less space. Okay, so these kind of things still needs to be done, because the guest operating systems don't know that they are being virtualized. Okay, good. So memory virtualization, again, with the help of the hardware, it becomes more efficient. And finally, let's talk about the I/O virtualization. So with the I/O, always we start with the secondary storage disks. Okay, you might think that remember, this is our disk as a linear structure. I have partition number 1 and I have partition number 2 and partition number 3. You might say that this is an NT file system. This is a FAT file system. This is a ext3 file system, etc. Goes that way. You might say that, why don't we make this the partition for the virtual operating system 1, virtual operating system 2, virtual operating system 3, etc. But the thing is that you might have many virtual machines, sometimes hundreds. Okay, and you may not have that many partitions on your operating system. So instead of using this idea, the usual solution is use a special file on the hypervisor, okay, for each machine, for each guest operating system, and each guest operating system is going to use those files as their physical disk. Okay, so I added one more layer of virtualization to represent the files. This is going to be very similar to what you are going to do for your homework number 4, because in your homework number 4 you are going to virtualize the FAT12 file system, and you are going to keep all of your data on a single Linux file. Okay, so you could do anything you want with your new file system, adding files, deleting files, modifying them, erasing them, creating them, etc. You could do whatever you want, and it will be very similar to that. So the hypervisor is going to use special files to represent the file system of the whole guest operating system. That's what the I/O virtualization does for the disks. Okay, but you might say that this is not the only I/O devices. We have many other I/O devices, and the thing is that each I/O device, we need to use the DMA device, and each I/O device will need their own interrupts and etc. For that, again, we need the I/O support. And luckily, before the I/O virtualization, we did not talk about this at all before, but we have this I/O MMU. Okay, What's IOMMU? IOMMU like an MMU, memory management unit. Okay. What is the main task of the MMU? MMU virtualizes the main memory, right? So remember from the beginning of the semester, we have our CPU. Okay. Our CPU is connected to the system bus like this. And this is our memory. Our memory is like this. And then I have my other I/O devices, like what do we have? Okay, these are my I/O devices, and this is my MMU, memory management unit. CPU goes through this MMU to see the memory and other stuff. Okay, so this is for making the logical address spaces possible. Okay, MMU is a very big part of the whole computer system, and we do a lot of things with the MMU for our operating systems. Okay, we know this. The similar problems exist for the I/O devices. Okay, the I/O devices, they have their own addresses. Okay, and for example, the DMA device, DMA device, okay, the DMA device is connected to the system bus like that, okay. DMA device needs to transfer some data from the I/O devices to the memory, but how does the DMA device know about the logical addresses? Okay, so the DMA device uses this IOMMU hardware. Okay, the IOMMU hardware uses this memory virtualization technique. Okay, and it is basically used for virtualizing the I/O the same way the MMU virtualizes the memory. Okay, and the IO MMU can handle DMA addressing. So this is already done for our regular operating system procedures. So we are going to take advantage of it. And we are going to use this hardware for the IO virtualization. Okay, IO virtualization. So what do I mean by IO virtualization? Each guest operating system can have its own IO addressing, and from operating system to operating system this IO addressing will change, and I am going to program this IO MMU when I switch from one operating system to another operating system during the input outputs. Okay, so IO addressing is done. The same problem happens for the interrupts. Okay, whenever a keyboard, let's say a keyboard interrupt has happened. So what am I going to do with the keyboard interrupt? Which operating system is going to take it? Okay, and how do I handle it? Okay, so I need to handle this interrupts, and I need to virtualize the interrupts too. Okay, so the modern IO MMUs, again, they support interrupt remapping. Remember how I handled interrupts? When the interrupt happened, there is an interrupt vector. And I choose one function from that interrupt vector and I execute it. Okay, if I keep a separate interrupt vector for each guest operating system, then that means that I can switch between the operating systems freely, and my interrupts are going to be handled nicely between the guest operating system. Okay, this is called interrupt remapping. Okay, it's called interrupt remapping. And interrupt remapping is going to be handled by the IOMMUs. As you see, for the sake of virtualization, they made many hardware modifications available for us, not for the CPU virtualization, but for the I/O virtualization and the memory virtualization, and we take advantage of them. And these kind of modifications or the hardware support did not happen in a single year. It took maybe 10-15 years to develop, and it took maybe 10-15 years for all the people to agree on some kind of a standard for the virtualization. But when it is done, we started using these kind of virtualizations in a very effective way. Even on the simplest hardware, okay, I can use these kind of virtualizations, and that will make things a lot easier for me. Okay, as I said before, virtualizations, when I started this chapter, virtualization is important for us because it is used a lot. But as operating system, as students, as researchers, as designers who study the operating systems, it is important for us to understand the real operating system. Okay, you know that the operating system has to manage the whole box. I mean, the I have to abstract all the hardware resources. I have to abstract away the details of the CPU, memory, and the I/O. Okay, if you take this abstraction idea one level further, you have the virtualization. Okay, if you understand what the virtualization does and the problems of virtualization, you understand the real operating system concepts. That's why I like to introduce this chapter to you. I could have talked more about deadlocks and etc. I didn't want to do that because nobody uses deadlocks, but virtualization is used a lot. Okay, it is useful for you to know how the virtualization is done. Actually, when you understand the virtualization, you understand the operating systems. That's the second thing that I like you to know about the virtualization. I guess that's it for the last lecture. And if I go back to the original, okay, if I go back to the original introduction chapter, where is my original introduction chapter? Yeah, introduction here. We started this semester. We started this semester with these slides. Okay, why we are studying operating systems and the definition of the operating systems. Okay, we said that there are two things. One is operating system, the abstract computer hardware true interfaces. Okay, it abstracts the CPU, the complicated parts of the CPU and the memory and the I/O devices. Okay, hides the messy details of the underlying hardware, and each user thinks that they have the whole computer to themselves, and the computer is a very nice place to work on. Everything is easy. I have my CPU, I have my linear address space, and I can do the input output by asking somebody who knows how to do the input output. So abstracting away the details of the hardware, also I need to manage the resources. Okay, I need to manage the resources, managing all these components. Okay, managing the resources are the second thing. So that's what we did the whole semester. Okay, to abstract away the hardware details, you need to know about the hardware details. Okay, to manage the resources, you need to know about the details of the resources. So we looked at the details of the hardware and the resources, and we looked at the techniques to abstract away them or managing them. That's what we did the whole semester. And if you remember, I had to skip lots of stuff. The operating system, the book already skips many stuff, and I am skipping many stuff from the book. Operating system is a very deep topic to study, but this is just an introductory course to operating system. And we ended up talking about the whole picture at the end of the semester through virtualization And that was a nice chapter to conclude this course. So you need to know about the operating system, as I said before, because we use operating systems a lot. You need to understand them. Okay, that's the first reason why we studied operating system. The second reason is we need to know about the history of the computer science so that we know why people made those decisions. Sometimes those decisions are not very logical or very wise decisions. Okay, sometimes those decisions made because of the because of the commercial or money related causes. Okay, the corporations make those decisions and they are not perfectly good decisions. Okay, in terms of computer science or the computer engineering, but they are done. So we need to understand how the things happened so that we can understand why we are doing this kind of stuff in today's world. And finally, operating systems are large pieces of code. They are pieces of code and large pieces of code, and this is a very nice opportunity to study those kind of large code systems. Millions of tens of millions of lines of code. Okay, as large as it gets, and that was another opportunity for us. Okay, so I'm going to conclude my course for this semester. And if you have any questions, I can take your questions right now. Otherwise, I will stop and I will see you on the final day, final exam day. Read the rest of the book. The rest of the book is nicely written. Well, it is not as nice as the first 5, 6 chapters because when you get more advanced, things are not things are not that organized. You always have to talk about the specific operating systems and etc. But they are very informative, and I would definitely read the rest of the book. You don't have to read it very carefully like you are taking a course, okay? Just read it to get the idea what that kind of thing is, okay? I already covered chapter number 5, 6, and 7. Okay, definitely read about the security and multiple processor systems. And these chapters about Unix, Linux, and Android, okay, they are already important. And chapter 11 it talks about Windows 8. Windows 8 is not that different from Windows 10. They are using almost the same ideas. But when you look at them, okay, it doesn't talk much about the structure of the whole Windows. It's like a dictionary. Okay, it gives you lots of structure definition, but it doesn't tell you why they are doing that. Okay, it's not like an operating system book. It's like a user manual kind of like, or the reference manual kind of thing. Okay, so but it's still useful. You will the many things we are going to make lots of sense when you read these chapters about the specific operating system. You go there, for example, look at the memory management. Okay, okay, like the memory management system calls, and you are going to make sense out of these calls because we already covered what many of those things mean. Okay, so Windows has to use those general ideas, but usually they give them different names. Okay, good. Okay, if there are no questions, then I will stop here and I will see you on the finals
Thank
exam
you,
day.
sir, for everything.
Sure. Okay, thank you, Mohammed. You asked lots of questions. I felt lonely many times. You saved me by your questions. I didn't feel lonely.
Hopefully the questions made sense, sir.
Well, your questions were as sensible as my my talking, so we are even. Okay, thank you everybody.
Teşekkürler hocam.
Teşekkürler Mesut.
Thank you so
Thank you,
much.
sir.
Thank you.
Thank you, sir. Have a nice day.
You too. Bye. Your final homework is not a very difficult one, but it will take some time, and it's going to be a very good opportunity to learn about the file system. So while you are studying your file system, you implement it, and you'll be fine. Okay, see you.